Recording's rolling. It is Tuesday, September 30th. We're going to do a Kahoot on Newton's second law of motion. We did first law the other day. That was law of inertia. The second law, this is the mathematical one. So acceleration is net force acting on mass. So if you can identify the net force and divide by the mass, they'll tell you how much it accelerates. Okay? And then whatever time we have left, we'll work more on these puzzles. And as long as you guys are following along, whatever we do in class, that's what I'll pick up from you guys on Friday. And so these will be on Friday, and then you guys get some points of the grade book by Friday. So flip over to Kahoot. Oh yeah, oh yeah, look at you guys. All right, so Newton's second law of motion. F equals ma. Acceleration produced by a net force on an object. Yeah, all those are true. Yeah, so the acceleration would have a direction. It's also the same direction as the net force, so same direction. Right. It's also directly proportional to the net force. That means if you triple the net force, the acceleration would also triple. So triple, triple. Right? But also inversely proportional to the mass. That means if you put the same force on a larger and larger mass, there's less and less acceleration. So hence the divide, right? Acceleration is force divided by mass. Yeah, so all those statements are true. All right, I got points on the board. Ooh, yeah. When an object reaches terminal velocity, what is its acceleration? Yeah, 0 meters per second squared. So remember what that means is here, draw this out for you guys. Okay. So actually, you know what? Now I'm remembering it. My AP class had a question about raindrops falling at terminal velocity. So you can model a raindrop as a sphere. I'm actually showing you guys an AP question, right? Maybe you have small raindrops, big raindrops, but when they reach terminal velocity, is it true the weight down is balanced out by a drag force pulling it up? Okay. Okay. So yeah, that's pretty much it. Right. Now their extension question was here. I'll show you what. The question was, what's the terminal speed in proportion to the radius of the raindrop? That's why I have different size raindrops. Right. So yeah, that's a little fun to dig out that answer. But yeah. Okay. All right. So then when the force is balanced, it'll go down at constant speed, hence zero acceleration. All right. I've got Anna, Gavin, Isabella, Kai, Caitlin. A book weighs 4 newtons when it's held at rest in your hands. What's the net force on the book? Net force. Yeah, zero. Zero. Right, 0 newtons. So here, draw that. So here's a book. It probably looks about like that. Book. Right, so you're holding it in your hands at rest. Now, at rest is key because that means that it's not moving. Okay. And so I think the free body diagram would look like this. Right. The book has a weight. The book has maybe a normal force from your hands holding it up. And that's it. Right. So the net force is zero because there are two forces, but they zero out. Yeah, that's it. So there's zero net force. Hence zero acceleration. Right. All right, got Caitlin, Cole, Gavin, Anna, Isabella. Girl pulls a 10-kilogram wagon with a force of 20 newtons. What's the acceleration? Yeah, that's it. So you just divide them, right? 20 newtons on 10 kilograms. Now, maybe this is a little simplified because we're assuming whether forces or maybe if there's no friction force. Right? Right. So here, maybe I'm thinking like kind of like this. Right, we got a wagon. If you pull it strictly horizontally with the force of wait, what was the force? I just forgot. 20 newtons. Yeah. All right. Thank you. Yeah. 20 newtons. Was the mass 10 kilograms? I think. Right. So you pop in here 20 newtons on 10 kilograms. Yeah, that gives you two. That'd be meters per second squared, wouldn't it? Right. That. Right. No, this wagon could have some other forces. So, oh guys, how about this? If it has a mass of 10 kilograms, how much does it weigh on Earth? How much does it weigh? Could weight be equal to mg? Right? That's normally what I label it, right? Mg. Okay. 98. Okay, yeah, 98 newtons. Okay. I might round that to like about 100, right? Because we got 10 kilograms. It per gravity you either pick 9.8 or 10. So if we do 10 times 10, yeah, that'd be about 100 newtons weight. Okay, and there'd also be a normal force from the ground, F sub n normal force, which in this case would also be well, it would balance it out, right? So it has to be 100 newtons up, 100 down, 100 up. Okay. Uh, now, as long as there's no frictional force, then if you pull 20 newtons, if I made it the scale, I guess that should be shorter. You guys get the idea, right? Okay. There's Newton's second law right here. Newton's second law. Okay. It's like that. Boom. We go. We got Kai, Caitlin, Cole, Isabella, Anna. Rock is thrown vertically into the air. At the very top of its trajectory, the net force on it is. Weight. Yeah, just as weight. Right? And that's true whether or not you consider air drag. Right? So if you throw a rock straight up, right, and like right at the top of this path, so it's like straight up followed by straight down. Right? But, if there is no air drag, then the net force is definitely its weight. Because in fact, from the moment it leaves your hand until the moment right before you catch it, the only force on it is its weight. Right? If you consider air drag, it's a bit more complicated. But at the very top, guys, at the very top, it's not actually moving for one instant. Isn't that true? Right? If that's true, well, drag force turns out to be proportional to the speed squared. So if the speed is zero, then the drag force is also zero. So that would still be the free body diagram, even in the air. Yeah. So the net force is just its weight. That's it. Its weight. Hey, you guys good with these? All right, boom. I got Cole, Gavin, Caitlin, Anna, Isabella. Spot. Particle is accelerated through space by a 10 Newton force. Suddenly, the particle encounters a second force, also 10 newtons, in the opposite direction to that of the first force. What does the particle do? Is it brought to a rapid halt? Does it gradually decelerate to a halt? Does it continue at the speed it had when it encountered the second force? Does it accelerate to speeds approaching the speed of light? Which one of those is true? Uh, yeah, so I'm looking for continuous at the speed it had when it encountered the second force. And I'll show you guys why. Okay, so start off with the scenario. Like, here's the particle. Yeah. Right, here's the particle. Maybe it's in deep space, and there's just one force on it. Maybe it's pushing it to the right. Right. So if there is a net force, would it be speeding up? Yeah. So it's going faster, faster, faster. It's like through space. Right. And then suddenly it encounters a second force that's also 10 newtons, but the opposite direction. So 10 newtons this way. Guys, now what is the net force? What is that? 0 newtons. Right. Now, it had already sped up to some speed, like leading up until it encountered this force. So it was already in motion. Okay? So it's already in motion. As if an object is already in motion and it has zero net force, then won't it just keep going at whatever velocity? Right, I see. Right. That kind of reminds me of let's see if I can find this here. There's a specific free body diagram. I'm thinking, here it is, here it is. Okay. You guys remember the rocket in deep space at constant velocity, and there was no force at all, right? But if you have two forces that cancel out, that's effectively the same net force. If they're here, okay, just keep going. Right. You know what this kind of reminds me of too? I remember back when I was taking physics in high school, there was a question I missed on a test, and it went like this. Suppose some guy's like sliding down a rope. Okay, you guys see this rope right here? Sliding down a rope. Right. And maybe his weight is more than the friction force that's resisting. So he's like speeding up. Okay. And then he grips the rope tighter. And when he does that, it suddenly brings it to a point where his weight down is canceled out by the friction force. This would be a friction force between his hands and the rope. Okay. So he was in motion, right? He was in motion, and he grips a little tighter, and then this happens. Okay. So this is equilibrium, right? Equilibrium. And guys, what's the net force in this case? Yeah, zero. So zero net force. Right? So what does this guy do? Does he suddenly stop? No. Right? He goes down at constant velocity. So this is really sort of the same thing, isn't it? It's just this turns sideways. Sure. Same thing, isn't it? I guess yeah. Good thing. Right. For him to come to a stop, what he would actually have to do is he have to grip the rope so tight that the friction force is actually more than his weight. And then that would slow him down and allow him to come to a stop. Okay. So you need something like that. You guys get that one? All right. I got Anna, Talia, Cole, Gavin, Isabella. Ooh, pressure. Ooh. Uh, yeah, force per area. Okay, so force per unit area. And there's some units I think you guys probably know with this. Guys, what's the metric unit for pressure? Okay, well, that's like the American unit, PSI. Could that be pounds per square inch? PSI, pounds per square inch. Right. Now, the metric unit could that go newtons per square meter? Right. It's also called pascals. Yeah. Did I show you guys the bed of nails? Did you guys see that? Yeah. Yeah. Okay. All right. That was like a pressure demo, right? Because it's like, well, you have some weight, but some force on one nail, on 1,000 nails. Right. If you increase the number of nails, that's like increasing the area. So more area would be like less pressure, and so that would be better, right? That's better to be on 1,000 nails than one nail. Right. All right. I got Caitlin, Talia, Isabella, Cole, Gavin. Oh, next question. See how many guys were following. What's the unit for pressure? Yeah, there you go. Right. So it's force per area, wasn't it? So the newtons per square meter. We got. Now, newtons per meter is something. Here, we'll go through all the other ones. Okay. Guys, does anybody know what newtons per meter is? Or what can be used to quantify? You guys remember spring constant? Like how stiff is a spring? Okay. I've got an activity for later this week. I'll have you guys figure out what's the spring constant, all those spring scales that you guys work with. Okay. Like if it's a really stiff spring, it doesn't take a lot of force just to stretch it a little bit. There'd be a lot of newtons per meter, wouldn't it? Ooh. Some of you guys picked meters per second squared. What does that describe in physics? Acceleration. Aha. Okay. And then just plain newtons, so that would just be a force. Okay, like pushing or pulling on something. All right. Got Caitlin, Talia, Isabella, Gavin, Cole. Oh man, it is a race for first. A tennis ball and a solid steel ball with the same diameter are dropped at the same time. Which ball has the greater force acting on it? Greater force, right? If you're holding them in your hand, which would be heavier? That's another way to say it. Okay. Yeah. Okay. Yeah. Here. How many guys out here? Okay. So, okay. So they said a tennis ball and a solid steel ball. They don't make it smell like shiny. Okay. So could this be T for tennis and S for steel? Like I said. Okay. Now, if the same diameter, I guess they have the same volume, the both spheres. Okay. But guys, if you hold these in your hand, would the steel like super heavy? And the tennis ball is kind of like I said. Okay. So if I drop them at the same time, then maybe the tennis ball has a free body diagram that looks like this. The steel ball has a free body diagram that looks like this. Right? Different weight. Different. There's different mass, different weight. Is it? You know what? This sort of reminds me. Um, what if you drop these off a cliff? Right. So you drop them at the same time off the cliff. They're both falling down. Um, and you guys remember air drag? So the force of the air drag is proportional to the speed squared. Right? The full equation, by the way, looks like there's like a 1/2 coefficient of drag, whatever. Right? then the density of the air, the cross-sectional area like plowing through the air, which is like this area, which would be the same for both, because it's the same size, right? Times the speed squared. That's like more complete. So, okay, so if these both kind of reach terminal velocity at the same time, which one, or does one of these reach terminal velocity first? Which one? The tennis ball. Yeah. Okay. Let's say they're both like picking up speed at the same rate, just to really simplify it. Okay. Let's say they pick up so much speed. Right. You run this equation. They got same coefficient of drag. They're both spheres. Same density of air. They're both falling through the same air. The same cross sectional area because they're both same size. Okay. But the speed. Right. Let's say they pick up to the same speed. Okay. Right. And it happens to match uh, the weight of the tennis ball. So this would be F drag right here. Right? And this would be the same F drag over here. Again, just to kind of simplify it. Do you guys see that? Right. Ah, guys, does that tennis ball, is it going down at terminal velocity, like constant velocity? It would be, because there's zero net force on it. So it's not accelerating anymore when you consider the air drag. Okay. But the steel ball, is there still a net force on the steel ball? Yeah. So is the steel ball still accelerating? Sure is. Yeah, sure is. Okay. So I think in this case, when you do consider the air drag, now do both these balls hit the ground at the same time anymore? No. I don't think so. Which one hits the ground first? Steel ball, because it pops in the air more easily, right? It's more difficult to reach terminal velocity. Okay. And maybe if it's a super tall cliff, like high Mount Everest, it might eventually reach terminal velocity. Okay. But this drag force has to really build up and it has to be going really fast for that to happen. Yeah. Right, so in a vacuum, they hit the ground at the same time. But through the air, the heavier ball actually does hit the ground faster. Yeah, it's true. All right. We got Caitlin, Talia, Isabella, Cole, Gavin. Woo! Woo! Tight race for first. Question 10. Oh, there we go. Tennis ball, solid steel ball, same diameter, drop same time. In the absence of air resistance, so we're in a vacuum. In a vacuum, which ball has the greater acceleration? In a vacuum. Okay, yeah, it would be the same. You guys remember they both accelerate at 10 meters per second squared, right? Okay, yeah. And the here I'm gonna maybe do a little overkill, but I really want to make sure you guys get it because you guys know it'd be the same. Okay, and the sort of physics way to do this is okay, go back to tennis ball, shiny steel ball. Okay. You say, well, wait, the tennis ball has a smaller weight, and the steel ball has a larger weight. Okay, but the tennis ball has a smaller mass and a steel ball has a larger mass. Here, maybe I'll make this capital M for mass of the steel ball to distinguish the two, right? Okay. So do you guys remember Newton's second law? Acceleration is net force on mass. Okay. And in this case, the net force is each weight. So for the tennis ball, it'd be mg over m. And then the acceleration is just g. For the steel ball, acceleration is big mg over big M. It's it's still G, right? Right. Yeah. So they both in a vacuum they would fall together. Okay, so in a vacuum, right? There's no air drag. All right. All right. Let's get that. All right. Oh yeah. Um, you pull horizontally on a desk with 150 newtons. The desk does not move. The friction force must be 150 newtons. Now you pull with 250 newtons. The desk slides at constant velocity. What's the friction force? There's some time to think about that one. Here, give you guys a hint. Guys, constant velocity. What's the net force for constant velocity? Uh, yeah, it would be 250 newtons, same as your pulling. And I'll draw up a picture why, show you guys why. Okay. Okay, so let's say that starts here. This dot maybe be approximately the center mass. The center mass, by the way, doesn't actually have to be on the object. It's just like where sort of the central location. Okay. So Because this desk could have a weight and a normal force acting on it. Okay, those will balance out later. Right? And then you're pulling to the right with like an applied force of 150 newtons, and the desk doesn't move. Well, if it doesn't move, that is definitely an example of equilibrium. So this friction force would be also 150 newtons. Right? That was the setup. That was the premise, right? Now to help you guys out, guys, is this a static or a kinetic friction? If it's not even moving at all, that's static. Guys, that's static friction. Right? Right. And then new scenario, right? I bet this dust has the same weight as it did before, the same normal force holding it up, right? But now you pull with 250 newtons. So F pull equals 250 newtons. Okay. It says the desk slides at constant velocity. Yes, constant velocity. What's the acceleration equal to? Uh, zero meters per second squared, which means the net force must be zero, which means that this friction force, Fr, must also be, well, it must have to balance this one out. Is that true? So it'll be 250, and that'll be newtons. Is that true? Right, that's true. Right. Right. Is this friction static or kinetic? No, it's sliding across the floor. It's kinetic. It's kinetic. Aha. Yeah. Kinetic friction. Right. So it's sort of a different category friction. Right. Here, remind you guys of this. That looks a lot like this, doesn't it? Isn't that basically what I just drew? Right. So, okay, constant velocity also. Constant velocity, all the forces balance out. Okay. So, in the kinetic case, the friction force is coefficient of kinetic friction times the normal force. So if you knew the weight of this thing, I bet we could figure out coefficient of friction. Right? Now, remember in the static case, remember this inequality, it sort of like builds up. So if you put a small force, it doesn't move. Put a medium force, it doesn't move. Right? It takes a good amount of force to break that initial friction. Right? Like that. All right. All right, guys, good. All right. Got Isabella, Caitlin, Cole, Talia, Gavin. Angle of incline with the block resting on it increases. What happens to the normal force? Right, so it's got some time. I'm gonna flip my screen. I'll flip it back. Right. So you guys see a block on an incline, and if I increase that angle, what happens to this blue force right here? That's the normal force, isn't it? Blue force. Ooh, all right, yeah, it's got a decrease, right? Right. So, right, so the weight of the block stays the same. The normal force changes, right? Oh, here I got one just for this case, So see, you can start off with the block on just a horizontal table, and in that case, wouldn't the normal force actually be equal to its weight? Is that true? But then you tip it to some angle, right? And that changes from well, it starts out its weight, right? To its weight times cosine of theta. Guys, cosine of theta is not between 0 and 1, like zero point 0.9 or zero point 0.8 or zero point 0.7. Okay, so it is getting smaller. And then if you continue, so maybe it's like 45 degrees here and like 60 degrees here, and you keep increasing it, okay, you could eventually go to like a vertical wall. And if you put a block against a vertical wall and let it go, I bet that normal force just like goes to zero, wouldn't it? Right? You guys see this blue force get a little smaller, a little smaller, a little smaller. Right? So you jump up that angle. Imagine a little animation there. Right? We got Caitlin, Bruce, Cole, Gavin, Talia. Speeding truck locks its brakes and skids to a stop. If the truck's mass were doubled, the skidding distance would be like the skidding to a stop distance. Skidding to a stop. Here's one of the question asked about like if you drive to the grocery store and fill your car with groceries, what happens to the braking distance? Ooh, same braking distance. Same. Uh, ooh. Got a couple of geniuses out there. Right? Okay. And so, guys, it's related to this one here. So, right here's a car braking stop. Now it's moving to the right, but it's braking. So, right here's the force was weight, normal force, and the friction force would be resisting its motion to slow it down. Is that true? Right. Right. So here's Newton's second law of motion. F equals ma. And the net force here is the friction force. I did go back and put in a negative sign, so I updated this about a week ago. Okay. And that friction force is coefficient of friction times normal force. The normal force balances out the weight, so I can substitute there. Okay. But guys, what variable cancels right here? The mass of the car. So the rate the car's allowed to slow down, that's acceleration, right, actually is independent of the mass. So if you have a light car versus a heavy car, right, what matters is the coefficient of friction between the tires of the road and the gravity field. Okay? That tells you the rate the car's allowed to slow down. Okay, guys got that? Okay. Now this concept is going to show up a few weeks from now. Oh look, I got a different poster with the same title, but it's got a green banner. You guys haven't seen this yet. Right? It's braking distance. So when we eventually do conservation of energy, I'll show you guys how to find braking distance. Right? Now braking distance. It turns out, yeah, coefficient of friction and gravity field matter. Right? Also matters how fast the car was initially going. So you do have to control for that. What's the initial speed? Right? Turns out the braking distance is proportional to the speed squared. So yeah, that's a future topic. You guys will see that. Okay. Actually, you could kind of solve that already if you combine this with kinematic. Okay, because couldn't you do this? Can you figure out the acceleration of the car, which would be negative because it's slowed down? Okay. And then you can say, I wonder what is braking distance, this x right here, as a function of the initial speed of the car. Okay. But again, mass doesn't show up anywhere, and that's kind of the point of this particular question. Okay. The mass of the car doesn't actually matter. Yeah. Oh, we got Caitlin, Bruce, Cole, Gavin, Talia. If the force acting on a cart doubles, what happens to its acceleration? How was it? Yeah, so you guys said double, right? Like double. Hey, I overthink. Emphasize this here. Okay, force doubles. Okay. Here, maybe I should have pulled this one out before I even started the Kahoot, right? Right. This is the theme of the entire Kahoot that we're doing. Right, so acceleration is net force on mass. So if you double the net force, you double the acceleration. You guys got that? Yeah. Okay. Boom. All right. Okay. Hi, Gavin, Cole, Bruce, Talia. Suppose a cart's being moved by a force. If suddenly a load is dumped in the cart so that the cart's mass doubles, ooh, now it's more massive. What happens to the acceleration? Here, guys, right here. If you double this mass, okay, for example, write some numbers down. So, what if you had a 12 Newton force on a 1 kilogram mass? What would the acceleration be? 12 meters per second squared. Right? What if you to put the same force on a 2 kilogram mass? See, I doubled the mass. Now what's that? 6 meters per second squared. You see, by doubling the mass, you get half the final acceleration. Is that two? Right? Okay, so oh yeah, look at you guys. Look at that. All right, thanks. All right, got Anna, Cole, Gavin, Bruce, Talia. You're on a frozen pond. The ice starts to crack. You lie down and begin to crawl. Ooh, you're gonna Google snowshoes while you guys are thinking about that. Snowshoes. Yeah, decrease the pressure. If you lie down to begin to crawl, are you so like increasing the area that you're in contact with the ice? Right. Right. So this also here, look at this guy. Maybe there's like 5 feet of snow under him. Right? They can walk across. See those big old snowshoes? Right? Now he can't really change his weight. He's got a lot of weight. That's a lot of force. Right? But he can change the area on the snow that that force is acting. Right? By one of these big old snowshoes. You know, plop, plop, plop right across the snow. Right? So similar idea. And then here's another perspective. Here's the equation. I'll view this. You guys know pressure is force per unit area. Okay, so you can't really change your weight, but if you increase that area, that would be decreasing the number of pascals, decreasing the pressure. About like that. Got Kai, Anna, Bruce, Gavin, Talia. Ooh. Oh, look at you guys. 8,400, 85. Ooh, what a race for first. 20 Newton falling object encounters 4 newtons of air resistance. What's the net force? Yeah, 16 newtons is the next net force. Right. Here, I got a follow-up question. Isn't that this right here? That's not right there, right? 20 newtons, 4 newtons. Right. Guys, if this weighs 20 newtons, what is the mass of this object right here? About
2 kilograms.
2 kilograms. Ah, doesn't 2 kilograms weigh 20 newtons? Right. Right, true. Right. So if that's true, you guys just told me the sum of forces is 16 newtons, right? Net force, 20 minus 4. And it's on a 2 kilogram object. Guys, how much is this object accelerating as it's falling down? Accelerating. Uh-huh. 8 meters per second squared. Yeah. Okay. Because it's like 16 newtons on 2 kilograms. That's like 8 meters per second squared. Okay. Remember, if there was no air drag, this would be accelerating at 10 meters per second squared. But now because there's air drag, it's got to be less than 10. There it is. It's 8 meters per second squared. So it's still accelerating, still picking up speed, but the air drag is continuing to increase also. But at that particular snapshot, yeah, that's what that looks like. Okay. Got Cole, Anna, Bruce, Talia, Gavin. Ooh, you guys over 9,000. You pull horizontally on a 50 kilogram crate with a 350 Newton force, and the friction force is 200 newtons. What's the acceleration of the crate? It's called the soft screen while you guys are solving it. Gotta write this one down. 250. Ooh, all right, guys, doing pretty good. All right, so, all right, well, right, you got this drawn right here. All right, so we got this mass right here is 50 kilograms. Got 50 kilogram crate. Okay. By the way, I'm going to throw in some extra forces that you don't really use all this. Because with this weight, mg would be like 500 newtons. Is that true? And the normal force would balance that out at 500 newtons. That's true, right? Okay. But really to solve this, you need the pulling force right here and this friction force right here. That tells you the net force. Guys, what's the net force? 150. Yeah. Okay, so it's 350 minus 200, which is like 150. Okay, and that's acting on a 50 kilogram mass. Okay, so that's 150 over 50. That's, well, meters per second squared. So it's like 3 meters per second squared. So there you go. And so net force on mass, put it on two accelerates. I got a follow-up question. Can anybody tell me what is the coefficient of friction? Anybody see that? What is the coefficient of friction? Is that friction force compared to normal force? Is that what that is? Who knows? What's the coefficient of friction?
2.5.
0.4. Yeah, 0.4. Okay. This is this 200 Newton friction force divided by this 500 Newton normal force. Right? Which you didn't need before, but you do need now to solve this question. Huh? Yeah. 2 over 5, that's like 0.4. Yeah. The Newtons cancel. 0.4. It's the coefficient of friction. Okay. You guys remember in your lab, what else labs you guys were, did you guys get a coefficient of friction about 0.2, 0.3, somewhere in there? Okay. And this is 0.4. Ooh. All right. I got Cole, Anna, Talia, Bruce, Gavin. Oh, it's still a tight race. Anybody can win this. 2 questions left. Jumbo jet cruises at constant velocity when the total thrust of its engines is 50,000 newtons. How much air resistance acts on the jet? Air resistance. Yeah, 50,000 newtons. Yeah. Okay. I give you guys a picture. Isn't that this right here? Okay. So if the thrust force is 50,000 newtons and it's constant velocity, right, there must be zero net force, so the drag force must also be 50,000. So these two canceling out. Yeah, that's it. 50,000 forward, 50,000 backward. Yeah, right. Boom. Awesome. I got Cole, Anna, Talia, Bruce, and Gavin. Nicholas backward. Streak of 3. On fire. 20 Newton falling object encounters 20 newtons of air resistance. What's the net force? 20 down, 20 up. Oh yeah. Right. Zero net force, right? Hey, guys, would that be terminal velocity? Yeah. So it would be an equilibrium, be going as fast as it's going to be going. Terminal velocity. All right, to the podium. With the hey, get that monkey off. With the bronze, Talia. With the silver, Bruce. And the gold, the Gavin. All right, nice job. Nice job. Oh yeah. All right, so here we have a few minutes left, so let's knock out just a couple more of these. See. So last one I did with you guys was number 30. Okay, next one up. You were handed a spring that is 0.3 meters long. Hey, 0.3 meters. Do you guys have an object within reach that's 0.3 meters long? Hey, this is 0.3 meters. Hey, look at that. It's right there. Your ruler. Ruler. So you have a spring that's that long. You hang the spring from a hook on the ceiling and attach a 0.5 kilogram mass, which, by the way, that's this one right here, right? Okay. So you hang this from a spring, and on the other end, right? The spring is stretched 0.32 meters. What's the spring constant? Now, I'll give you guys an activity later this week that's pretty similar to this. I'm gonna have you guys figure out what's the spring constant in every one of these springs right here. Right? So you pull some force and stretch it so far. Right? Right. So how stiff is the spring is another way to say that. Right. So number 35. Right. So we got ceiling. Right. We got a spring. We hang that lab mass. Right. So this is a mass of 0.50 kilograms. Right. And then this whole thing stretches. I don't think my picture's to scale, but you guys can name it. Okay. This whole thing stretches 0.32 meters. Actually, that's not far off. Right? This is the initial length was 0.30 meters. Okay. So, guys, this is a job for Hooke's Law. Let's see if I can find that one real fast. Yeah, here we go. I kind of have two for Hooke's Law. I've the one I've been using for many years. And there's also a restoring force interpretation. Okay. So some version of F equals kx, right? Something like that. Okay. So The force you put on a spring is equal to kx. Okay. Now, if it stretches this far, suppose it's in equilibrium at this point. So at this point, I think there's two forces on it, and its weight down would be balanced by the spring force up. Is that true? Oh yeah.
It tends to stretch like 3 years, so does it stretch?
Oh, stretch, spring, like actually, you know what? I see what you're getting at. You're saying that like the full length might be 0.32. Yeah, let's do that instead. Let me start over. I like that interpretation. Okay, so like the full length would be 0.32 because then we can actually incorporate the initial length. Yeah, I wasn't thinking about it that way, but I think you're right. Okay, so let's do the initial length is 0.30 meters. Okay, and then right the additional stretch maybe it only goes down to like here. Okay, so now well, right. Guys, that would make the change and like equal to what? Yeah, 0.02 meters. Right? Couldn't that be like 2 centimeters? Like 2 centimeters? Like that much? Okay. Okay, so that's like a pretty stiff spring. Yeah, that's it. Okay. So the mass was 0.50 kilograms. Okay. We got wait, can I use this one here? Okay. Okay, so this has a weight pulling down and a spring force pulling back. Okay. If it's just hanging there at rest, then that would be an example of equilibrium. So then can I say the spring force is balanced by the weight? So they do the same value, right? Okay. So I could say the spring force up minus the weight down goes to 0 newtons for equilibrium. Okay. Spring force is equal to kx. And add over the weight that equals mg. Okay. Okay. The question is, what's the spring constant of spring? How stiff is the spring? So can I divide over x? So the spring constant is mg over x. Right? Now we can just plug the numbers in. Kind of running out of room there. Yeah, more paper. This. Okay. All right, you guys following so far? Guys good? Okay. So the spring constant would be, okay, I got a 0.5 kilogram mass. Earth gravity we'll call about 10 meters per second squared. So there's the weight. And it stretches by 0.02 meters. So that's what 0.5 times 10 is 5 or 0.02. Okay. I'm looking at 250, and that would be newtons per meter. So the spring constant of spring would be 250 newtons per meter. Okay. Um, by the way, a side thought here. I forget exactly what the spring constants in these scales are, but this is about the order of magnitude. So I think it's approximately one of these springs right here. Okay. So if this was like a really long spring and you were to hang this from it, actually you can kind of do that right here, kind of. Okay. Okay, so this is stretch it by some amount. Stretches just some amount, doesn't it? Right? Actually, I wonder if it's actually this red one. Yeah. Oh, yeah. I think somewhere between the brown one and the red one, because the stretch is by maybe 1 or 2 centimeters right here with this weight. All right, so probably pretty close to that. All right, so check. Okay, number 36, a spring scale device that uses a spring with a known spring constant to measure the weight of objects. They have a spring scale with the spring constant of 10 newtons per meter. Okay, so this time they're giving you the spring constant. That's a really tiny spring constant. Okay. So that means you put on a 10 Newton force and it would stretch a whole meter. You guys see that? To stretch it 1 meter, you only need 10 newtons. Okay, so that's almost like a slinky almost. Right? How much will the spring stretch when a 15 Newton weight is hung from one end? Right. Well, I know 10 newtons would stretch it a meter. So 15 newtons is not going to stretch it like more than a meter, or something like that. Okay. So we can go back to Hooke's law again. Hooke's law. Do F equals Kx. Okay. We'll just do that. Okay. So in this case, they said a 15 Newton weight. So in place of the force, I put 15 Newtons. They said the K is 10 Newtons per meter. So goes right there, right there. Yeah. Okay. And then the question is, how much does it stretch? Okay. Solve for this X right here. Okay. Now, it's going to come out to some number of meters. Oh, Actually, what? I don't need a calculator for that. Guys, what's the answer? Yeah, 15 over 10, 1.45. And then the units cancel. Get meters. Yeah, that's it. Right. 1.5 meters. Right, you guys good? Right, number, well, at least we'll read 46. A dog is pulling an empty sled attached by a harness parallel to the ground in the snow. The sled's moving with constant velocity. The mass of the sled is 1.2 kilograms. The coefficient of friction is 0.2. They said coefficient of static friction. Right. But that wouldn't be applicable if it's moving at some constant velocity. So I think they meant to say coefficient of kinetic friction. Let's treat that as a typo. Right. So coefficient of kinetic friction, you guys get that? Is 0.2. Determine the harness tension, right? Which we could do, but the bell's going to ring in like a minute. So I don't want to really run out of time here. So let's just do this. Change the word static to kinetic. And then kinetic. Yeah, we got 3 days left this week. So we got a few days to solve some more of these. Right? So we'll solve that one next opportunity, and then maybe some from back. All right, and otherwise, that's a wrap on today.